There is a lie so big, so deeply rooted in the minds of billions of people around the planet, that when you discover the truth, you will question absolutely everything you ever thought you knew about the universe. And this lie involves the most extreme, most mysterious, and most misunderstood objects in all of cosmic existence: black holes. And when Neil deGrasse Tyson decided to expose this lie in a series of explanations that went viral around the world, millions of people were in absolute shock because they realized that the mental image they carried about these phenomena was completely, fundamentally, and irredeemably wrong. Not just in minor details or technical nuances, but in the very essence of what a black hole really is and how it really works. And today, I'm going to take you on a complete journey through that revelation. I'm going to destroy every bit of that lie that has been implanted in your mind by decades of misrepresentations in movies, TV shows, poorly produced documentaries, and oversimplified explanations. And in place of that lie, I'm going to construct for you the scientific truth that is infinitely more fascinating, stranger, and more wonderful than any fiction ever invented. Because the real universe doesn't need exaggerations or distortions to be absolutely spectacular. It's already bizarre enough on its own, and black holes are perhaps the greatest proof of this that exists. Before I reveal what exactly this lie is, I need you to understand the context of how it spread and why practically everyone believes it. Because understanding the origin of a misconception is the first step to definitively eliminating it from your mind. And this lie was born from a combination of oversimplifications, poorly chosen metaphors, and the natural tendency of the human brain to try to fit extraordinary phenomena into familiar categories. The problem is that black holes don't fit into any familiar category. They are so different from anything in our experience everyday life that any attempt to describe them using simple analogies inevitably distorts reality. And that is exactly what has happened over decades of well-intentioned but fundamentally problematic science communication. And now the time has come to correct this historical error and show you what physics really tells us about these extraordinary objects. The lie I'm talking about is the conception that black holes are like gigantic cosmic vacuum cleaners that violently suck in everything around them, like hungry gravitational eddies that chase stars and planets to devour them, like cosmic monsters with insatiable appetites that will eventually swallow the entire universe if we're unlucky enough. This image is so powerful, so cinematic, so perfectly suited to creating dramatic tension in science fiction films that it has taken hold in the imagination. Collective as absolute truth. And when people think of black holes, they immediately envision this predatory entity sucking up stars in dramatic spirals, spaceships being pulled against their will to certain death, and all the matter in the universe being inevitably consumed by these insatiable monsters. But this image is completely wrong, fundamentally mistaken in almost every way. And Neil deGrasse Tyson has spent years of his career patiently explaining why this conception is not only incorrect, but also diminishes the true magnificence of what black holes really are. And if you are one of those people who feel that genuine fascination with the cosmos, who love having their conceptions challenged and expanded, who want to be part of a community of curious people exploring the mysteries of the universe together, then subscribe to the channel now, because this journey today is just the beginning. We have many more fascinating scientific revelations to share with you, many more surprising truths that will transform your understanding of the cosmos. And I promise that every minute spent here will expand your mind in ways you never imagined. Be possible. So let's start destroying this lie piece by piece. And to do that, we need to first understand what gravity really is, because this is where the confusion begins, and without this fundamental understanding, Nothing I say about black holes will make complete sense, and the truth about gravity is much stranger and much more beautiful than most people realize. For centuries, ever since Isaac Newton formulated his law of universal gravitation in the late 17th century, humanity has understood gravity as a force of attraction between objects with mass, an invisible force that pulls objects toward each other through empty space. And this description works extraordinarily well for almost all practical situations. It allows we can calculate orbits of planets, trajectories of rockets, the fall of objects to Earth, but it is fundamentally incomplete. It describes what gravity does without explaining what gravity actually is, and it was Albert Einstein who completely revolutionized our understanding by publishing his theory of general relativity in 1915, revealing that gravity is not a force in the traditional sense. It is a manifestation of the curvature of space-time itself, caused by the presence of mass and energy. Let me explain this to you with an analogy that will clarify everything. Imagine a stretched trampoline, that flexible surface where children jump. Now imagine that you place a bowling ball in the center of this trampoline. What happens? The surface curves, creates a depression around the ball. And if you now roll a marble across the surface of the trampoline, it will not follow a straight line. It will curve its trajectory towards the bowling ball. Not because the bowling ball is pulling the marble with some invisible force, but simply because the marble is following the most natural path through a surface that is curved. And this is essentially what happens in real space-time. Massive objects like stars and planets curve the fabric of space-time around them. And other objects follow this curvature, which we perceive as gravitational attraction. And the more massive the object, the more pronounced the curvature, the more intense the effect we call gravity. Now here is the crucial point that dispels the lie about black holes. The intensity of gravity you experience at a given distance from an object depends only on two things: the total mass of that object and its distance to the center of mass. It doesn't matter at all whether that mass is spread out like a diffuse cloud the size of millions of kilometers or compressed into an infinitely dense point. If the total mass is the same and its distance to the center is the same, the gravity you experience will be exactly identical. And that means something absolutely revolutionary to our understanding of black holes that most people never noticed. If you could magically replace the sun with a black hole of exactly the same mass, you know what would happen to the Earth and all the other planets in the solar system. Absolutely nothing in terms of gravitation. The Earth would continue to orbit in exactly the same way, at the same distance, with the same orbital period of approximately 365 days. The other planets would continue their normal orbits. No objects would suddenly be sucked towards the new black hole. Because the gravity at that distance would be exactly the same as it was when the sun was there. The only difference would be that we would no longer have sunlight and would freeze to death. But this is a thermal problem, not a gravitational one. And this revelation should immediately destroy the image of the black hole as a cosmic vacuum cleaner. Because a black hole has no special gravitational power beyond what any object with the same mass would have. It simply concentrates that mass in a much smaller region of space. Neil deGrasse Tyson uses a brilliant analogy to explain this. He says, imagine you are 100 meters away from an elephant. You feel the gravity of that elephant, which is tiny but theoretically exists. Now imagine you could compress that entire elephant into a point the size of an atom without changing the total mass. The gravity you would feel 100 meters away would be exactly the same. It wouldn't change at all. What changes is what happens when you get too close, because with the normal elephant, you would eventually bump into it. But with the elephant compressed, you could get much closer to the center of mass, and then you would experience much more intense gravity. And that is exactly the situation with black holes. They are no more gravitationally powerful than normal objects of the same mass at the same distance. They simply allow you to get much closer to the center of mass without bumping into any solid surface, and it is this extreme proximity that creates the extraordinary phenomena that we associate with black holes. This understanding completely changes the way we should think about these objects. They are not cosmic predators hunting victims. They are simply regions of extreme curvature of space-time where the laws of physics operate in radically different ways than we are used to, and far from being destructive entities that threaten the universe. They are extraordinary natural laboratories where we can study the limits of known physics and perhaps discover completely new principles about the nature of reality. But now that we've debunked the first part of the lie, let's explore what really happens when something is wrong and approaches a black hole. Because although they are not vacuum cleaners that suck up everything indiscriminately, what happens nearby is genuinely extraordinary and much more fascinating than the simplified caricature we have been sold. To understand the phenomena that occur near a black hole, we first need to understand a fundamental structure called the event horizon. And this is one of the most misunderstood and difficult to visualize concepts in all of physics, so I'm going to spend a lot of time explaining it properly. The event horizon is not a physical surface. It is not a solid wall or a tangible membrane that you could touch or see directly. It is a mathematical boundary defined by the geometry of space-time around the black hole. Specifically, it is the distance from the center of the black hole at which the speed required to escape gravity exceeds the speed of light. And since nothing in the universe can travel faster than light, approximately 300,000 kilometers per second, anything that crosses this boundary is permanently confined to fall toward the center without any possibility of return. No matter how much energy you have, no matter how powerful your rockets, once inside the event horizon, your fate is sealed by the fabric of space-time itself. But here's something amazing that Neil deGrasse Tyson loves to explain. If you were falling toward a sufficiently large supermassive black hole, you could cross the event horizon without immediately realizing that anything special had happened. There would be no visible line in space. There would be no abrupt transition. There would not necessarily be any immediate sign that you had just crossed a boundary from which there is no return. And this is deeply counterintuitive because we expect such significant boundaries to be somehow noticeable. But the event horizon is defined by global properties of the space-time, not by local conditions that you could measure at the time of crossing, and this subtlety is one of the most unsettling and fascinating characteristics of black holes. Now let's talk about one of the most extraordinary phenomena that occur in the vicinity of black holes, something that completely defies our intuition about the nature of time. And that phenomenon is gravitational time dilation, an effect predicted by Einstein's general relativity and confirmed experimentally countless times with extraordinary precision. The basic idea is that time passes at different rates depending on the intensity of the gravitational field in which you are immersed. The more intense the gravitational field, the slower time passes in relation to regions of weaker gravity. And under normal conditions, this effect is minuscule. GPS satellites, for example, which orbit the Earth at altitudes where gravity is slightly weaker than on the surface, experience a temporal difference of about 45 microseconds per day in relation to clocks on the surface. And, although it seems insignificant, this difference is large enough to cause positioning errors of several kilometers if not corrected. So all GPS technology relies on relativistic corrections that would have been considered science fiction a century ago. But, in the vicinity of a black hole, time dilation becomes extreme in ways that defy any analogy with everyday experience. Imagine you have a friend who decides to take a trip very close to the event horizon of a supermassive black hole. While you remain at a safe distance, your friend spends a few hours exploring this region of extreme gravity, feeling time pass normally from your own vantage point, making observations, perhaps taking some cosmic photos, and then returns to meet you as you compare clocks. The discrepancy is staggering. For every hour your friend experienced, days, weeks, months, or even years could have passed for you, depending on how close to the event horizon he got. And this is not an illusion of perception. It is the physical reality of time working differently in different regions of space-time. Your friend actually aged less than you. His cells actually divided fewer times. His heart actually beat fewer times. Time genuinely passed slower for him. This discovery about black holes impacted scientists all over the world, and I'm wondering, where are you watching right now? Comment on your city or country. It's absolutely incredible to think that we are all connected in this same universe trying to understand it better. That people from different continents, speaking different languages, living completely different realities, are all fascinated by the same cosmic mysteries. And this collective search for knowledge is one of the most beautiful expressions of human curiosity. Continuing our exploration, there is an even more dramatic phenomenon that occurs when objects approach black holes, especially smaller stellar mass black holes. And this phenomenon has an appropriately grotesque name: spaghettification. And it represents one of the most violent ways in which matter can be destroyed in the entire universe. To understand spaghettification, we need to talk about tidal forces, which are the differences in gravitational intensity between different parts of an extended object. Here on Earth, we experience tidal forces due to the Moon. The side of the Earth closest to the Moon is pulled a little more intensely than the center of the Earth, which in turn is pulled a little more intensely than the opposite side. And this difference causes the ocean tides we see every day. The effect is subtle, because the Moon is very far away, and the gravitational difference across the Earth's diameter is small. But in the vicinity of a black hole, especially a compact black hole of stellar mass, the tidal forces become unimaginably intense. Imagine you are falling towards a black hole feet first. The gravity pulling on your feet is significantly stronger than the gravity pulling on your head, because your feet are closer to the center of the black hole. And this difference creates a stretching force that pulls you in the vertical direction. At the same time, parts of your body that are laterally offset from the center are pulled in slightly converging directions in toward the center, creating a horizontal compressive force. The net result is that you would literally be stretched vertically while being squeezed horizontally, turning into a long, thin thread of matter stretching toward the black hole. Just like spaghetti being pulled down a drain, hence the name spaghettification. The intensity of this effect depends critically on the size of the black hole. And here we encounter one of the most counterintuitive paradoxes in black hole physics. Smaller black holes are actually more violent in the vicinity of the event horizon than larger black holes. For a typical stellar mass black hole, perhaps 10 times the mass of the Sun, the tidal forces become lethal long before you reach the event horizon. You would be spaghettified thousands of kilometers away. But for a supermassive black hole, like the one that exists at the center of our galaxy, at 4 million times the mass of the Sun, the event horizon is so far from the center that tidal forces at that distance are relatively mild. You could theoretically cross the event horizon of a large enough supermassive black hole without being immediately destroyed. Spaghettification would come later, as you continued falling towards the central singularity. Speaking of the singularity, this is perhaps the most mysterious and least understood concept in all of black hole physics, and it represents the absolute limit of our current knowledge, the point where our most successful theories completely fail and produce results that make no physical sense. The singularity is the center of the black hole, the point where all matter crossing the event horizon eventually falls, and according to the equations of general relativity, it is a point of infinite density and infinite curvature of space-time, where the laws of physics as we know them cease to operate. And when physicists get infinities in their equations, it usually means that the theory is incomplete, that we are extrapolating beyond the theory's domain of validity, and we need a deeper understanding to describe what actually happens. Most physicists believe that a complete theory of quantum gravity, which would unify Einstein's general relativity with quantum mechanics, would solve the singularity problem, probably by showing that on extremely small scales, quantum effects prevent the formation of truly infinite densities. But such a theory does not yet exist in complete form. Although promising candidates such as string theory and loop quantum gravity are being actively developed, and the singularity remains a reminder that our understanding of the universe, although extraordinarily sophisticated, is fundamentally incomplete. Now, I want to tell you about one of the most revolutionary and counterintuitive discoveries about black holes, a discovery made by Stephen Hawking in 1974 that shocked the scientific community and continues to generate heated debate to this day. And that discovery is that black holes are not completely black. They glow, albeit very dimly, emitting a form of radiation that we now call Hawking radiation. To understand Hawking radiation, we need to briefly delve into the strange world of quantum mechanics, where the vacuum is not actually empty, but buzzes with activity. Quantum field theory tells us that even in seemingly empty space, pairs of particles and antiparticles are constantly being created and destroyed in infinitesimal fractions of a second. These so-called quantum fluctuations are normally imperceptible because the pairs annihilate each other almost instantly. But near the event horizon of a black hole, something extraordinary can happen. Imagine a pair of particles being created right at the edge of the event horizon. It is possible for one particle to fall within the horizon while the other escapes into outer space. Normally, these particles would have to come together and annihilate, but the boundary of the event horizon separates them permanently. The particle that escapes becomes real and carries energy away from the black hole. This energy cannot come from nowhere because it would violate conservation of energy. So it effectively comes from the black hole itself, slightly reducing its mass. And if you watch this process happening repeatedly throughout the time, the black hole is slowly emitting radiation and shrinking. It is evaporating. The evaporation rate of a black hole is inversely proportional to the square of its mass, which means that smaller black holes evaporate much more quickly than larger black holes. For a typical stellar mass black hole, the time required for complete evaporation would be inconceivable, much longer than the current age of the universe multiplied by itself dozens of times. Timescales so long that we have no adequate words to describe them, but for hypothetical microscopic black holes. Evaporation could happen in fractions of a second, accompanied by a burst of energy. This discovery by Hawking created one of the greatest paradoxes in modern theoretical physics, known as the black hole information paradox. And this paradox touches on fundamental questions about the nature of reality that we have not yet fully resolved. Profound questions that involve the compatibility between two of the most successful theories in physics, general relativity and quantum mechanics, and whose resolution will likely require a profound revision of our understanding of space, time, and information. The problem is this: the fundamental laws of quantum mechanics state that information can never be truly destroyed. It can be transformed, scrambled, rendered practically inaccessible. But the full information about the state of a system must be preserved. This is essential for the equations of quantum mechanics to work and make correct predictions. But when matter falls into a black hole, it appears that all information about that matter is lost behind the event horizon, forever inaccessible to the outside universe. And when the black hole eventually evaporates through radiation Hawking, the emitted radiation appears to be purely thermal, with no information about what originally fell into the black hole. So, what happens to all this information? Is it genuinely destroyed in violation of fundamental principles of physics? Or does it somehow escape, or is preserved in ways we do not yet understand? This paradox has occupied the brightest minds in theoretical physics for decades, generating fascinating proposals and heated debates. Some suggested answers include the idea that information is in fact encoded in subtle ways in Hawking radiation through extremely delicate quantum correlations, or that information is stored in some kind of remnant left after complete evaporation, or that our understanding of the event horizon is fundamentally incorrect and needs to be revised. And although significant progress has been made, especially through ideas like holographic correspondence, which I will discuss shortly, the paradox is not yet completely resolved, and its resolution will likely teach us something profound about the connection between gravity, quantum mechanics, and the fundamental nature of information. Now I want to explore an aspect of black holes that is often overlooked in popular explanations but is absolutely crucial to our understanding of the universe: the role that black holes play in the formation and evolution of galaxies. Because far from being mere isolated destructive objects, supermassive black holes are at the heart of almost all large galaxies and actively influence their development over billions of years. The discovery that virtually all large galaxies host supermassive black holes at their centers is one of the most important revelations in astronomy in recent decades. And not only that, there is a surprising and between the mass of the central black hole and properties of the host galaxy, specifically the mass of the galactic bulge, the densest central region of the galaxy. And this correlation is so precise that it implies some kind of co-evolution. The black hole and its host galaxy have somehow grown together, influencing each other's development over billions of years in a complex gravitational dance. But how exactly a black hole that occupies an infinitesimal fraction of the volume of a galaxy can influence the development of this entire enormous structure? The answer lies in periods of intense activity called quasars, or active galactic nuclei. When large amounts of matter are falling into the central black hole, this matter does not fall directly in a simple way. It first forms an accretion disk rotating at speeds close to the speed of light. And the friction within this disk heats the matter to temperatures of millions of degrees, causing it to emit extraordinary amounts of energy in all frequencies of the electromagnetic spectrum, from radio waves to gamma rays. And in some cases, jets of relativistic particles are launched perpendicular to the disk at speeds approaching that of light, extending millions of light years into intergalactic space. This enormous energy released during episodes of intense activity can have profound effects on the host galaxy, heating interstellar gas and preventing it from collapsing to form new stars, or alternatively compressing clouds of gas and triggering waves of star formation, feeding and feedback over billions of years. And here's something I find particularly fascinating in the theory I discuss: the supermassive black hole at the center of our own galaxy, the Milky Way, called the Sagittarius A*, is currently relatively quiet. It is not in a phase of intense activity like the distant quasars we observe, but there is evidence that it was much more active in the past. Gigantic bubbles of hot gas extending above and below the galactic plane, discovered by the Fermi Gamma Ray Telescope, suggest that there was a burst of activity at the galactic center a few million years ago, and it's possible that our hominid ancestors, walking across the African savannas, could look up into the night sky and see the galactic center shining much more brightly than we see it today, a view we wish we could recapture. I want to now tell you about one of the most exciting moments in the recent history of astronomy, a moment that Neil deGrasse Tyson publicly celebrated as one of the greatest scientific achievements of the 21st century. And that moment was the first direct detection of gravitational waves by the LIGO collaboration in September 2015, announced to the world in February 2016. Gravitational waves are literally ripples in the very fabric of space-time, predicted by Albert Einstein in 1916 as a consequence of his theory of general relativity. When massive objects accelerate, especially when they move in asymmetric patterns, they create disturbances in space-time that propagate outward at the speed of light, just like ripples in a lake when you throw a stone. And although Einstein predicted the existence of these waves over a century ago, He himself thought they would be impossible to detect because even cataclysmic events produce extraordinarily weak waves when they reach Earth. But LIGO physicists and engineers achieved the seemingly impossible. They built detectors so sensitive that they can measure distortions of space smaller than the diameter of a proton. And on September 14, 2015, these detectors recorded a signal that perfectly matched theoretical predictions for the merger of two black holes. Two objects with masses of approximately 36 and 29 solar masses spiraling towards each other over millions of years, spinning faster and faster as they get closer, until they finally collide and merge into a single larger black hole. And in the last instant before the merger, these two black holes were orbiting each other hundreds of times per second. And the energy released in gravitational waves in that brief moment was equivalent to approximately 3 solar masses being converted into pure space-time ripple energy. More energy than all the stars in the observable universe combined were emitting at that instant in the form of light. Gravitational waves from this merger traveled through the cosmos for the more than 1 billion years until they reached Earth, where they caused a distortion of space so minuscule that it would be equivalent to changing the distance between Earth and the nearest star by a fraction of the diameter of an atom. And yet our instruments were able to detect this incomprehensibly small change, and the shape of the signal exactly matched theoretical predictions for merging black holes, simultaneously confirming the existence of gravitational waves and the existence of spiraling and merging binary black holes. Since that first historic detection, dozens of gravitational wave events have been detected, including mergers of black holes of various masses, mergers of neutron stars that are almost black holes, and even mixed events where a black hole merges with a neutron star. And each detection teaches us something new about the population of compact objects in the universe, about how they form and evolve, about the frequency of mergers, and about the astrophysical processes that create them. And as if the detection of gravitational waves wasn't revolutionary enough, in April 2019, humanity achieved another historic milestone: the first direct image of a black hole, captured by the Event Horizon Telescope, and this image visually confirmed what decades of theory had predicted, showing us for the first time the shadow of an event horizon. The Event Horizon Telescope is not a single telescope, but an international collaboration that has connected radio telescopes around the world to create a virtual telescope the size of the Earth, using a technique called very long baseline interferometry. This approach allows you to achieve extraordinary angular resolutions, enough to see details on scales equivalent to reading a newspaper in New York while you are in Paris. And the first image showed the supermassive black hole at the center of the galaxy Messier 87, at 55 million light-years away, a monster with a mass equivalent to 6.5 billion suns. The image revealed a bright ring of superheated matter orbiting the black hole at speeds approaching the speed of light, with a dark region in the center corresponding to the shadow of the event horizon. The light from that side of space simply cannot reach us because it was captured by the black hole, and the shape of the ring, slightly asymmetrical due to relativistic effects such as Doppler beaming, precisely matched theoretical predictions based on general relativity, yet another spectacular confirmation that Einstein was right more than a century ago. This image represents much more than just a pretty photograph. It is a direct validation of over 100 years of physical theory, a confirmation that our mathematical equations correctly describe phenomena in extreme conditions that are completely beyond any earthly experience. And this agreement between theoretical prediction and observation is what gives science its extraordinary power. We are not just inventing stories about the cosmos. We are discovering truths that withstand the most rigorous tests we can devise. Think about what this means in practical terms. Physicists working with pen and paper, or more recently with computer simulations, We're able to predict exactly how a black hole should appear, what shape, what brightness structure, what kind of asymmetry, all before we had the technology to actually observe one, and when we finally managed to capture that image, it matched the predictions with remarkable accuracy. That's not magic. That's the power of the scientific method applied consistently over generations of researchers building on each other's work. In May 2022, the Event Horizon Telescope collaboration revealed an image of the much closer black hole to us, Sagittarius A*, the supermassive black hole at the center of our own galaxy, just 26,000 light-years away. And although it is much smaller than Messier's 87, at only about 4 million solar masses, the proximity means it appears at a similar angular size in the sky, and once again the image confirmed theoretical predictions, showing a bright ring, with a central dark shadow. Obtaining this image was extraordinarily challenging for reasons that perfectly illustrate the complexity of black hole physics. Unlike the black hole in Messier 87, which is relatively stable because its enormous mass means that any variation takes a long time to manifest itself. Hyperactive image in constant motion, scientists had to develop sophisticated image processing techniques to extract a stable average representation from continuously varying data. This difficulty also means that future observations of Sagittarius A** could potentially capture this variability in more detail, allowing us to see material rotating in near real time around the event horizon. And there are already plans to expand the Event Horizon Telescope with more observing stations and to operate at higher frequencies that will provide even better resolutions, meaning that the extraordinary images we have today are just the beginning of an era of direct observation of black holes that will reveal ever more stunning details. There is also the exciting possibility of creating movies of black holes, not just still images but sequences showing the evolution of material around the event horizon over time. And these dynamic observations will allow much more precise tests of general relativity in extreme conditions, potentially revealing subtle deviations from predictions that could point to new physics beyond Einstein. But I now want to explore some of the most speculative and fascinating frontiers of black hole physics, areas where established science meets still developing theory, and where the questions are as profound as the answers are elusive. And I will begin with an idea that connects black holes to the most fundamental questions about the nature of space, time, and information. In recent decades, theoretical physicists have discovered surprising connections between black hole physics and a seemingly unrelated area called quantum information theory. And these connections suggest that black holes can teach us something profound about the fundamental structure of reality, specifically about the nature of space-time itself. One of the most revolutionary ideas in this area is the holographic principle, which suggests that all the information contained in a region of space can be completely described by information encoded on the surface surrounding that region, just as a three-dimensional hologram is actually encoded on a two-dimensional surface. And this idea originally arose from black hole physics, from the observation that the entropy of a black hole, a measure of how much information it contains, is proportional to the area of its event horizon, not its volume, as would be expected if the information were distributed throughout the region. Interior. The most precise mathematical realization of this idea is the ADS-CFT correspondence, proposed by Juan Maldacena in 1997, which establishes an exact equivalence between certain gravitational theories in spaces with anti-de Sitter geometry and gravity-free quantum field theories living at the boundary of these spaces. In other words, in certain contexts, gravity and space-time itself can be seen as emerging from a more fundamental description that does not contain gravity, and black holes in this description correspond to thermal states in the border. Although the ADS-CFT correspondence has only been rigorously established for specific geometries that are different from our real universe, the lessons learned are profoundly influencing our understanding of how gravity and quantum mechanics can be unified. And many physicists believe that a version of this holography applies to our universe as well, suggesting that the space-time we inhabit may be a kind of holographic projection of information encoded on a distant boundary. Another fascinating frontier involves the possibility of using black holes as energy sources for sufficiently advanced civilizations, and although this is far beyond our current technological capabilities, the laws of physics apparently allow for this type of exploration, and the best-studied method is the Penrose process, proposed by physicist Roger Penrose in 1969. Rotating black holes, which are probably the majority of real astrophysical black holes, drag the space-time around them in a phenomenon called frame drag. And there is a region called the ergosphere, outside the event horizon, where this drag is so intense that nothing can remain still relative to distant stars. Everything is forced to rotate along with the black hole, and within this ergosphere, it is possible to extract rotational energy from the black hole through an ingenious process. The basic idea is to send an object into the ergosphere and split it into two parts. One part falls into the event horizon while the other is ejected back out, and if this is done correctly, the ejected part can come out with more energy than the original object had. The extra energy comes from the rotation of the BU black hole that slows down a little after each extraction, and theoretically, this process could continue until all of the black hole's rotational energy has been extracted, which could represent up to 29% of the black hole's total mass converted into usable energy. A sufficiently advanced civilization could build a megastructure around a rotating black hole to extract energy in this way on an industrial scale, enough energy to power an interstellar civilization for billions of years, long after all the normal stars have gone out. And this possibility shows that black holes are not just objects of destruction. They are potentially the last available energy sources in an aging universe, beacons of usefulness in a cosmos that would otherwise be plunging into eternal darkness. There is yet another speculative but fascinating possibility that involves black holes and time travel or connections between distant regions of space-time. And here we need to be very careful to distinguish between what established physics tells us, what speculative but mathematically consistent theories suggest, and what is pure science fiction with no basis in known physics. The mathematical solutions to Einstein's equations describing rotating black holes include fascinating geometric structures that would theoretically allow trajectories through the interior of the black hole to emerge in different regions of space-time, potentially connecting distant locations in the universe, or even different universes, through structures known as wormholes or Einstein-Rosen bridges. However, there are serious problems with this idea that probably make it impossible in practice. The idealized solutions assume perfectly symmetric and stable black holes that probably don't exist in nature. Any matter trying to pass through would disturb the structure in ways that would probably destroy it. And quantum effects that we ignore in these classical solutions probably have dramatic consequences. So although traversable wormholes are mathematically possible in certain circumstances, we have no evidence that they exist or can be constructed. And most physicists are skeptical about its viability. But there is a related possibility that is slightly more substantiated, though still highly speculative, the idea that the interior of a black hole could give rise to a new baby universe that expands in a similar way to our own Big Bang, but that is causally disconnected from the original universe except through the black hole that spawned it. And physicist Lee Smolin has proposed that this natural selection cosmology could explain why our universe seems so well-tuned to produce stars, complex elements, and life, if universes give rise to daughter universes through black holes, and the laws of physics vary slightly with each generation. So universes that produce more black holes would have more descendants, and the laws of physics would naturally evolve to favor the production of black holes, which in turn require massive stars that require complex chemistry that also allows life. I now want to address some of the most pressing open questions in black hole physics, questions that are being actively investigated by scientists around the world and whose resolution is likely to teach us something profound about the nature of reality. One of the most important questions concerns the nature of the singularity. At the center of the black hole, we know that the equations of general relativity produce infinities at that point, indicating that the theory is incomplete. But what actually happens there? Most physicists believe that quantum effects prevent the formation of truly infinite densities. But without a complete theory of quantum gravity, we cannot calculate exactly what replaces the classical singularity. It could be a region of extremely high but finite density. It could be a transition to a different phase of space-time. It could even, whether it is a connection to another universe, as Smolin's speculation suggests, we simply don't know yet. Another crucial open question concerns the final fate of a black hole as it evaporates through Hawking radiation. We know that the rate of evaporation increases as the black hole gets smaller, meaning that the final stages would be extremely fast and violent. But what exactly happens at the last instant, when the black hole has a mass comparable to the Planck mass and quantum gravitational effects completely dominate? Some physicists speculate that there may be some kind of stable remnant left, carrying all the information that the black hole has accumulated. Others think that the black hole disappears completely in one final explosion. Resolve this. The question requires theory that we do not yet possess. There is also the search for primordial black holes that could have formed not by the collapse of stars, but by extreme density fluctuations in the first moments after the Big Bang, when the universe was incredibly dense and hot. If these primordial black holes exist, they could have very varied masses, from much smaller than stars to much larger, and could potentially explain a fraction of the mysterious dark matter that we know exists but have never directly detected. And the detection of gravitational waves is providing new tools to search for evidence of these hypothetical objects. The idea of primordial black holes is particularly fascinating because they would have formed before the first stars, in the first seconds or fractions of a second after the Big Bang, when the universe was an extremely dense soup of energy and particles, and small density fluctuations in this primordial soup could have been amplified to the point of direct gravitational collapse, creating black holes without the need for a progenitor star. Depending on the exact moment they formed, these primordial black holes could have masses ranging from fractions of a gram to thousands of solar masses, a much wider range than black holes formed by stellar collapse, and very small black holes would have completely evaporated through Hawking radiation long ago. But those with masses above about 500 million tons would still exist today, roaming the cosmos like relics from the beginning of time. If primordial black holes with masses in the range of a few tens to a few hundred solar masses exist in significant quantities, they could explain some of the gravitational wave events detected by LIGO that involve black holes with masses greater than would be easy to explain through normal stellar evolution. And each new detection adds more data to test this hypothesis. Although so far, we have no definitive evidence for or against the existence of primordial black holes. There is also an intriguing possibility that very small primordial black holes, if they exist, could be detected through their final bursts of evaporation. The last moments of a black hole evaporating through Hawking radiation would be accompanied by a burst of high-energy gamma rays, and gamma-ray telescopes in operation around the world are watching for signals that could correspond to such events, although none have been conclusively detected so far, which places limits on how abundant these objects can be. Coming now to the end of our journey, I want to reflect on what this all means for us as human beings, trying to understand our place in the cosmos. Because when we contemplate objects so extreme, so far beyond everyday experience, we are forced to confront the limits of our intuition and expand our conception of what is possible. The lie we exposed at the beginning, The image of the black hole as a monstrous cosmic vacuum cleaner that devours everything indiscriminately was not only scientifically incorrect, it diminished the true magnificence of these objects by replacing the real complexity with a simplistic and frightening caricature. The truth is infinitely richer. Black holes are natural laboratories where the fundamental laws of physics are tested in extreme conditions. They are important builders of galaxies that influence the evolution of cosmic structures over billions of years. They are potential energy sources for the distant future of intelligent life. They are living enigmas that challenge our understanding and push us to develop deeper theories. They are windows into fundamental questions about the nature of space, time, and information. Neil deGrasse Tyson often talks about how the study of the cosmos inspires a unique blend of humility and empowerment. Humility because we realize how small and ephemeral we are compared to cosmic scales that span billions of light-years and billions of years, but also empowerment because this same human mind, inhabiting a fragile body on a tiny planet, has managed to unlock secrets of the universe that seem far beyond any relevance to our immediate survival. We have been able to predict the existence of black holes before. By observing them, we can photograph event horizons millions of light-years away. We can detect gravitational waves from mergers that happened billions of years ago. And this ability to understand is itself an extraordinary cosmic phenomenon that deserves to be celebrated. And if these revelations expanded your mind as much as they expanded mine when I first understood them, leave a like on this video, subscribe to the channel if you haven't already. Activate the notification bell, because we have many more mysteries of the universe to explore together, and share this video with that friend or family member who also loves science and would be fascinated by these truths about black holes. What aspect of black holes fascinated you most on this journey? Was it the time dilation that allows effective travel into the future? Was it spaghettification and its violent implications? Was it the information paradox and its connections to fundamental questions about the nature of reality? Was it the possibility of extracting energy from rotating black holes? Or was it some other aspect that we discussed? Comment below, because I love reading the comments and seeing which parts of these cosmic journeys resonate most with each person. And if you have questions about anything we discussed, you can also comment, and I will do my best to respond. Think about it. At some point, thousands of years ago, a human ancestor looked up at the night sky and wondered what those lights were. And that seemingly simple question began a journey of discovery that eventually led us to understand that some of those lights are accretion disks around black holes in distant galaxies. That space and time are aspects of a unified fabric that can be bent and distorted. That there are regions of the cosmos from which not even light can escape. That progression from mystery to understanding is the story of science in its finest form. Pure and black holes represent one of the most exciting chapters in this ongoing story. We are living in an extraordinary era of astronomy and physics. New discoveries are happening at a rapid pace. Ever more powerful instruments are being developed, and the coming decades promise revelations that will make what we discussed today seem like just the beginning. The Event Horizon Telescope is being expanded with more telescopes and observing frequencies. Gravitational wave detectors in space, like the upcoming LISA project, will make it possible to observe frequencies inaccessible from Earth. New ground and space telescopes will revolutionize our understanding of galaxies and their central black holes, and every advancement will open windows to aspects of the universe that we cannot even imagine today. And here is perhaps the most profound truth that emerges from all this exploration. The universe does not need our distortions or exaggerations to be extraordinary. Reality as revealed by physics is stranger, more beautiful and more awe-inspiring than any fiction. Real black holes are more fascinating than fictional black holes because they really exist. because the laws of physics really produce these extraordinary phenomena, because we can actually study them and learn from them. And this connection to reality gives our wonder a depth that no fantasy can match. The next time you look up at the night sky, you can look toward the center of the Milky Way, knowing that there, 26,000 light-years away, there exists a supermassive black hole around which stars orbit at breakneck speeds, where time passes differently than it does here, where fundamental questions about the nature of reality await answers. And this knowledge enriches the experience of contemplating the cosmos in ways our ancestors could not have imagined. You are part of a species that not only inhabits the universe, but is actively working to understand it. And that is extraordinary. But before I close, I want to leave you with some more deep thoughts about what the existence of black holes means for our understanding of the universe and ourselves, because I believe that science at its best not only informs us about curious facts, it profoundly transforms the way we see the world and our place in it. When Newton developed his laws of gravitation in the 17th century, he gave us tools to predict the motion of planets and calculate projectile trajectories. But he also gave us something deeper, a sense that the universe operates according to understandable rules, that we can decipher the secrets of nature through reason and observation, and that this worldview completely transformed human civilization in ways that go far beyond any specific practical application, ushering in an era of reason and discovery. When Einstein revolutionized our understanding of space and time in the early 20th century, he not only gave us more accurate equations, he completely transformed our conception of reality. He showed us that seemingly absolute concepts like space and time are in fact relative and intertwined. That gravity is not a force, but a manifestation of the geometry of the cosmos. And this conceptual revolution opened doors to technologies that would have been considered magic by previous generations. And now, when they behold black holes in all their complexity and strangeness, we are participating in the next stage of this great adventure of human knowledge. We are confronting phenomena that completely defy our intuition, that force us to abandon assumptions we didn't even know we had, that show us that the universe is much stranger and more wonderful than any human mind could have invented on its own. And there is something deeply democratic in this quest for knowledge. The laws of physics do not discriminate. The light from a distant black hole travels billions of light-years to reach our telescopes regardless of who is observing. The gravitational waves from cataclysmic mergers pass through all of us equally, and anyone with curiosity and a willingness to learn can participate in this adventure of discovery, can understand the same truths that occupy the minds of the world's greatest scientists. Neil deGrasse Tyson often emphasizes this democratizing aspect of science, the idea that the universe is open to anyone who wants to explore it, that there are no barriers other than our own willingness to question and investigate and learn. And black holes, perhaps more than any other phenomenon, exemplify this openness, because they are so strange and so removed from everyday experience that we all start from the same point of ignorance. We all need to rebuild our intuition from scratch to understand them. Think also about the deeper philosophical implications of what we've discussed, whether time actually passes at different rates in different regions of space-time, what this means for concepts like past, present, and future, whether information can somehow survive apparent destruction within a black hole, what this tells us about the fundamental nature of reality, whether black holes can create new universes or connect distant regions of space-time, what this suggests about the structure of the cosmos at scales we cannot directly observe. These questions may seem too abstract to have practical relevance, but the history of science teaches us again and again that the most fundamental questions about the nature of reality eventually lead to profound technological and social transformations. Quantum mechanics, which seemed completely disconnected from practical applications when it was developed, is now the basis of all modern electronics, of all the computers, phones, and medical devices we use every day. Special relativity, which seemed like a mathematical curiosity about extreme situations we would never encounter in real life, is now essential to the functioning of GPS and satellite communications. Who knows what technologies will emerge from our deepened understanding of black holes in the coming decades and centuries? Perhaps information storage methods inspired by the physics of event horizons, perhaps energy sources based on the principles we have discussed, perhaps even forms of space-time manipulation that today seem like pure science fiction. History suggests that the possibilities are limited only by our imagination and persistence. And there is something else I want to share before I close, something about the emotional experience of contemplating these extraordinary phenomena. Because science is not just about accumulating facts and equations, it is also about expanding our capacity for wonder, about cultivating a deeper appreciation for the complexity and beauty of the cosmos we inhabit. When you truly understand what is happening in the vicinity of a black hole, when you mentally visualize space-time bending into extreme configurations, when you imagine time slowing to a near standstill, when you contemplate the tidal forces that can stretch stars like spaghetti, when you consider the questions about information and entropy that we have not yet resolved, something shifts inside you. Your mind expands to accommodate possibilities that once seemed impossible. Your appreciation for the strangeness of the universe deepens, and you never look back. The night sky, in the same way. This kind of inner transformation is, I believe, one of the greatest gifts that science can offer. Not just knowledge in the sense of stored information, but a fundamental and transformative reconfiguration of how we perceive and relate to the reality around us. And black holes, because they are so extreme and so challenging to our intuition, are particularly powerful in this sense. They force us to abandon limited conceptions and embrace a much stranger and much more wonderful worldview. And so we come to the end of this journey, but in truth, we are only at the beginning, because each answer about black holes raises new questions. Each discovery opens doors to even deeper mysteries. And the adventure of reimagining the cosmos never really ends. It just keeps deepening and expanding as we develop new tools and new ideas. In the coming years and decades, we will see even more detailed images of black holes. We will detect gravitational waves from even more extreme events. We will develop theories that perhaps resolve the paradoxes we have discussed, and each advance will bring us closer to a complete understanding of these extraordinary objects, although I suspect there will always be more mysteries waiting beyond the horizon of our current knowledge. And you are part of this adventure. By watching this video, by seeking to understand these phenomena, by asking questions and questioning established conceptions, you are participating in the great human tradition of exploring the unknown. And this participation is significant regardless of whether you are a professional scientist or simply someone curious about the universe. Comment below if you have more questions about black holes, if you want me to explore a specific aspect in more detail in future videos, if there are other cosmic phenomena that fascinate you and that you would like to see explained. Because this channel is built by and for the community of curious people who share this passion for the cosmos, and your contributions are essential to shaping the content we produce. And if you've made it this far, if you've watched this entire journey from start to finish, you've demonstrated something important about yourself, a sustained attention span and genuine curiosity that are becoming increasingly rare in a world of constant distractions. And I genuinely appreciate that, because creating this content takes a lot of effort, and it only makes sense because there are people like you willing to engage deeply with these ideas. Thank you for coming with me on this journey through the mysteries of black holes. Thank you for your curiosity and your time, for being part of this community of explorers of the cosmos. And we will see you in the next fascinating video, where we will continue our adventure into the secrets of the universe. Until then, keep looking at the stars and asking why. Because this simple question is the seed of every great discovery. And the cosmos has infinite answers waiting for those with the courage and curiosity to seek them. And always remember, the biggest lie about black holes was not about technical details, it was about replacing magnificent reality with a simplistic caricature. And now that you know the truth, you will never see these extraordinary objects the same way again. You are part of the select group of people who understand black holes for what they really are, not as devouring monsters, but as elegant structures where the laws of physics reveal their deepest nature. And this knowledge is a treasure that no one can take from you, a permanent expansion of your understanding of the wondrous cosmos that created us and that we inhabit. Until next time.